Hello everyone, in the NPTEL online certification course software defined radio and its practical applications, we were discussing software defined radio components and architectures. So, we were basically discussing the RF transmitter and receiver and how they interact with each other. We have covered till now the digital portion which is the information in bits, its coding, its modulation and pulse shaping, so that the information is contained within a particular bandwidth. Once we have our information in the digital domain completely, then the next step comes to convert this digital information into analog information, because analog waveform is something which is actually travel across the medium and it is not the digital information. So, in digital to analog conversion, our data which is in digital domain, it can be represented in binary input. So, if you see here, our data can be represented as 8-bit data, 5-bit data, 4-bit data, and as we increase the number of number of bits we are using, it gives us more precision. So, for example, if we are having 8-bit data, we will be having 2 to the power 8 level. So, this will provide us the precision to represent that input digital information properly. This digital information is converted into analog by using digital to analog converter. This is the simple example of a digital to analog converter. This example shows a simple inverting circuit using op amp as digital to analog converter. So, what is the fundamental of this operation? If we look here, this operation amplifier, it has a V out and it is attached as a inverting mode. Now, that inverting voltage is given as 0 volt. With respect to this 0 volt, there are 3 branches, each branch contains a different resistance. So, the first branch contains resistance of R value R ohm, second one 2 R ohm, third one 4 R ohm. So, when we apply any voltage V1, V2, V3 on these branches, the current flowing through these branches becomes I1 is equal to V1 upon R, I2 equal to V2 upon 2R and I3 equal to V3 upon 4R. Now, because of the Norton's theorem, at any junction the incoming current should be equal to outgoing current. So, in this inverting section of the op amp, our total current is V out divided by R, which is actually the summation of I1, I2 and I3. So, V out upon R becomes V1 upon R plus V2 upon R plus V3 upon 4R. So, by doing this, we can write it like this. Right. So, if I choose my V1 is equal to V2 is equal to V3 equal to a fixed voltage, then basically V out can be given as V out upon R is equal to V upon R plus V upon 2R plus V upon 4R. Now, if our voltage V can have only 2 states, let us say V capital V volts, if on state and 0 volts if off state. So, if we look at it like this, and these are representing our relation between V out and incoming voltage V, we can see here that R will be cancelled, and basically it is a just relation between V out and V's. So, if this V voltage are represented as just a voltage, positive voltage V, and 0 when there is no voltage, it is off state, then we can see that first branch which is corresponding to V1 upon R, it has a direct relation to V out. The second value has it has impact of 1 upon 2 ratio with respect to our output, and this has 25%, 1/4 weightage with respect to output. So, if you look at this circuit and if you look at our binary digits, then we can say it is the least significant bit because it has lower weight there, and it is the MSB, most significant bit, because it has the most impact in this schematic. So, let us take this example. We are saying that whenever we have a signal, it is in on state, we will take 2 volts, and off state we will take 0 volts. So, for example of 3-bit DAC. Now, this 3-bit DAC will have 2 to the power 3 or 8 states basically. So, it can represent 8 different information by using 3 bits. So, let us say our input signal conditions are these: 0, the second level 0 0 1, 0 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. Okay. So, this is the digital information we have, which is representing a particular value, which is 0, 1, 2, 3, 4, 5, 6, 7. So, its actual value in the integer form can be from 0 to 7 here. Now, by applying this method for the 3-bit DAC, and this is the 3-bit DAC we are showing here, right? We have chosen our V to be equal to 2 volts. This V here, it becomes, for this example, it is 2 volts. Now, let us take our first example. Our V1, V2, V3, they all have 0 0 0. So, V out, which is given by this relation basically. So, let us again call it V1, V2, V3, because it is taking on off equation according to this relation, right. So, 0 0 0, our V out becomes, which is an analog output, right, which we can see from our eyes. So, it will become 0. Now, next is 0 0 1. So, this digit is 1 and the other twos are 0 0. So, what will be the value? It will be V3 divided by 4, because these two values are equal to 0. So, it will become 1 divided by 4 into 2. So, 1 into 2, which is the voltage, divided by 4, and it will be 0.5 volts. Okay, not 0.5, it will be minus 0.5 volts, because it is an inverter circuit. So, there is a correction, it should be negative here, as we can see here. So, basically for the second digit, this one will be 1, other two are 0. So, it will be 1 into 2 divided by 2. So, it will be minus 1 volts. What about next one? Now, these 2 will be 1 and it is 0. So, it will become 1 plus 1 by 4 into 2. So, minus 1.5 volts, right. So, if you keep calculating like this, it will be, the next one will be minus 2 volt. For this one it will be minus 2.5 volts. For this one it will be minus 3 volts, and for the last one it will be minus 3.5 volts. So, we can check for any random data. Let us say last example 1 1 1, it will be 1 plus 1 by 2 plus 1 by 4 into 2. So, let us do this calculation, 1 plus 1 by 2 plus 1 by 4 and all into 2. So, are we correct here? So, let us check it here. It will be 2 plus 1 plus 0.5 with a negative sign. So, it is correct here, right. So what we see here, as our digital signal is going from 0 to 7 values, we are actually able to see our voltage increasing. It was minus 0.5, it was 0, then minus 0.5, minus 1, minus 1.5. So it is stepwise, it is increasing. As we are representing our digital information in analog domain, we are able to see the variation, and there is a fixed step with each bit, and that step is of 0.5 volts. So this is a simple example of DAC, and there are some higher advanced examples for this also, but it gives us some idea that how we can convert from the digital to analog domain. Now in the series of this digital to analog conversion, now our data which we have with us, it is in analog domain and its frequency is still near 0. Now next step is actually frequency up conversion. So if you look here, why it is required and how we can do this. So frequency up conversion is related to the concept of antenna size. So basically antenna size should be the order of wavelength of transmitted signal, which is the size of the antenna is equal to lambda, which is the wavelength, and c is the speed of light, and this nu is the carrier frequency. So if we look here, suppose our carrier frequency is 1 kilohertz, right. So if I use 1 kilohertz, what should be my L? So let's say nu is 1 kilohertz or 1000 hertz. Then our length is actually 3 into 10 to the power 8 divided by 10 to the power 3. So it will be, or the length of this antenna will be 300 kilometers. So of course we don't want our antenna to be that big. As we keep increasing our frequency here, this L will go down. For example, we take a simple example of nu is equal to 2 gigahertz frequency, which is actually 2 into 10 to the power 9 hertz. What will be L in this case? L in this case will be 3 into 10 to the power 8. So if you calculate this, it is coming out to be 0.15 meter. Now it is a small antenna, and this is an antenna which we want to have. So working on the higher frequency gives us the smaller size of antenna. So this is one usefulness of choosing this. So frequency up conversion is actually required. Another point here is that we do require higher carrier frequencies, but those carrier frequency values, how to choose them, are decided by regulatory bodies. We just can't use any frequency for the transmission of the signal. We actually have to have some criteria decided that you can only transmit on this frequency. These are fixed frequency. For example, for WCDMA, WiMAX, LTE, they have separate bands there, and apart from that, this service providers, they are also given these particular frequency bands to deal with. So they cannot just simply transmit at any frequency. There are some bands for that. Now how do we do that? So we normally do this by using a component called mixer. So mixer is a component basically which is a nonlinear component. So in this we provide a LO frequency, and this is the incoming signal. It can be analog or RF, and if this is the input to this mixer, then output can be RF frequency plus LO frequency, RF frequency minus LO frequency, and its harmonics. And so on, other combinations also. So these are the outputs, they are the main outputs, and these are harmonics which have a little bit smaller amplitude. So basically, if I want to up convert my signal, I take this component, I filter out this component, and I suppress all these components. So the output frequency is the frequency of the incoming signal plus the frequency of LO. and the signal is up converted to a new frequency which is given by RF plus LO frequency. Similarly, at the receiver side, when you want to down convert, we choose this frequency. So in this case, we do the down conversion, we go to the lower frequency range. So frequency up conversion is done by using nonlinear mixers. Now based on up conversion, down conversion process, there are some few definitions in the literature which are used continuously. For example, passband signal is a signal which is at the higher frequency range. So in this, the same information is shifted to a higher frequency. So this carrier frequency FC is being shown, it is the passband. Baseband signal is basically the frequency in analog domain. However, information signal is near zero frequency. So whenever in the literature we hear about the baseband signal, it is a signal which is very near to baseband. Ideally it should be zero frequency, but practically carrier frequencies near zero are also considered baseband signal. The frequencies which can be handled in digital domain by using numerical oscillator, etc. Now these components we will be covering later in this course. Next stage is power amplification. So why do we require this power amplification? First of all, we have discussed that for the frequency up conversion, we convert the frequency of the signal to a higher frequency range. Now the problem with the high frequency is that high frequency signal, they encounter higher attenuation of the signal. So this again looking at the formula, that wavelength is equal to C upon nu. So C is the speed of light and nu is again our carrier frequency. If I increase the carrier frequency, my lambda, the wavelength, it goes down. So what does it mean actually? What is the wavelength actually? Wavelength is the distance travelled by a wave during to crest. So let us say this is our signal and it is repeating here, it crest is here. So normally whenever we talk about the signal processing, we have terms like time period, frequency. What is the time period? The time duration after which the signal repeats. Now wavelength is the distance travelled during that time when the crest has again received. So while the time period is dealing with the time, the lambda wavelength is dealing with the distance travelled. Now we have to take into account if our lambda is big, lambda is 300 kilometers, as I said before in our previous example. In this case, suppose my signal has to travel 300 kilometers in itself. In one lambda, one wavelength, in 300 kilometers, it will be showing its crest. This distance covered will be 300 kilometers. So during this duration, the signal has reached to peak at 2 instances. But if my lambda is small, for example the second example of the 0.15 meter, then while travelling this 300 kilometers, it has so many peaks to cover all this distance. So how many peaks? 300 kilometers divided by 0.15, that many crest will be there. So in this case 300 kilometers divided by 0.15 meter, this is the frequency how it will be repeating itself. So this many times this higher peaks will be dealing with the attenuation of the environment. So initially it has only this time period, while it was dealing with that attenuation, now it is dealing with those attenuation regularly. So most of the energy is dissipated into the environment in the form of heat and the signal power will go down. Now because signal power has gone down, we require the additional power to be given to the signal if it wants to reach that 300 kilometer distance theoretically, right. So that's why the power amplifier comes into picture. Power amplifier is boosting the power of the same signal. So now the signal is at a higher frequency because of this step of the frequency upconversion, and now we have given it the power, so it has also the power to reach that distance. Now once it is done, our signal has power, we transmit it through antenna. What is the antenna actually? We had shown earlier that when we were converting from digital to analog, then our signal was in the form of electrical signal. It can be current or voltage. Now antenna is something which captures and or transmits radio electromagnetic waves according to that electrical signal. So if we see the variation in voltage, it sends some radio electromagnetic waves according to that pattern of the input incoming voltage signal. So these electromagnetic waves, they can travel in the wireless media in the speed of light. So what is its main function? Main function is to transmit these signals through the media. Moreover, while designing these antennas, it also works as the band pass filter. It means it only allows a particular range of frequencies to pass. For others it does not work that well, so it attenuates those. So it works as the band pass filter. Moreover, it provides the directivity to the signal that at which location and in which direction the signal should go. So this is the main aim of the transmission. So once the signal has travelled through the wireless media and received by the receiver through antenna, then our RF domain data, our RF domain processing is done. So again we want to go back to analog domain and the digital domain so that we can retrieve our original information. So once we have received our data through the same antenna, again the antenna will have a particular bandwidth operation. It will get only a few selected frequencies of the incoming signal for which it is tuned, and when it is achieved, then the first step will be frequency down conversion. Now frequency down conversion is a step which is opposite of the frequency up conversion. As I showed you earlier, by using nonlinear mixer, we can select the subtractive component RF minus LO frequencies, and the frequency will come down to the analog domain. Now we have our analog domain signal which we have here in the transmitter section. So the same information we have here in the receiver section. Now we want to extract our digital data from this information. So this is a simple example of the analog to digital converter. Again there are much more sophisticated examples than this, but how the working of the ADC is done. So basically it is a simple comparator. What is happening in this circuit? Again it is a 3-bit ADC. So the example we had done earlier for the 3-bit DAC, it is opposite to that one. So our data is in the form of voltage and we want to get our binary digit out of it. So as we can see here, we have 8 inputs, one is 0 state and other 7 are from 1 to 7 states, and the output will be 3 bits digits. How does it actually works? That we make a table like this table here, and we know that when this particular voltage level is reached, then it means the value is 2 and it means our digital information should be this one. So basically we read this voltage values and we look in the table and we say, okay, it is near to this value, so it should be equivalent to this value, which is in binary domain should be 100 if it is the value is 4. So as we are showing here, this is the incoming voltage which is applied to the ADC, analog to digital converter. Then we have a reference voltage which we can tune beforehand, and it should be equal to the highest voltage reference level. For example, in previous example of DAC, our highest voltage level was 3.5 volts, actually minus 3.5 volts, so its polarity is different, that is the difference only. Now incoming signal is being applied here, and this V reference, it is attenuated by R. So some voltage will drop here, its twice will drop here, its thrice will drop here. So basically it will have all the full voltage, and then it will have 1/8 portion here, then 1/7 portion here, and so on. So voltage is dropping at the each node. Now what happens? These op-amp, they are working as a comparator. It means they compare the voltage level here with respect to incoming voltage. If this incoming voltage level matches with the V reference level, it outputs that level. So if this output voltage which is being shown here, here, it compares and it gives the output voltage, the highest level of output voltage achieved by this is considered by this 3-bit ADC. For example, let us say our input voltage is coming out to be minus 2.2 volt. So it is near to this value. Minus 2.2 volts. So our registers, they will be able to show this value, this value, this value, this value, but it will not be able to show these 3 values. So in this ADC, it will be seeing from the least significant bit, because it is dropping all the V reference here, it is the least significant bit. So it will be seeing 0 there, then it will be seeing -1, -1.5, -2, but it will not be giving any output from these, because this reference level is high, lower than these values. So among these 3 values, it will pick the highest one, which is the -2. According to that -2, it has a LUT which will read that it is value 4, and it will output 1, 1, 0, 0, and this will be fed to the digital circuit. So this is how we are able to see the analog component binary output for this analog signal. Now what is the limitation? It is very simple idea, it should work very fairly accurately. The limitation is that we can see here for 3-bit ADC we have to use 2 to the power 3 minus 1 comparators. If I want to use 8-bit ADC, it will be 2 to the power 8 minus 1 comparators. So complexity is increasing all the time. So based on this, there are some other kind of analog to digital converter. We are not covering all of them here, but you have basic idea that what kind of circuit can work here. So we have our data which is in digital domain here. Now once we have our data in digital domain and it is constrained within a particular bandwidth, we want to do something opposite of the pulse shaping. So we have a filter which is matched to the pulse shaping filter of the transmitter, and we get our data back in the digital domain, and then we have to demodulate it. So whatever modulation scheme we have chosen earlier, we have discussed PSK, so it can be QPSK, or it can be quadrature amplitude modulation. Now little discussion on QAM signals, because they are used basically in the LTE and LTE advanced concept. So earlier we have discussed about ASK, FSK and PSK, and we have seen the example of BPSK, 2 types of BPSK. Now among BPSK we had talked about constellation diagram. So you had 2 positions here showing the 2 phase positions. Now QAM signal, quadrature amplitude modulation, is basically which is taking care of this phase as well as amplitude modulation. QAM. So 16 QAM modulation, it is having actually phase locations here, rotations, right, means in this direction, that direction, in that direction, in that direction, as well as amplitude modulation, because some of them have this much R and some of them has separate R value. So amplitude modulation as well as phase modulation is there, and basically the data in the constellation diagram, it looks like this. Okay. So demodulation occurs so that we can read this value back from their constellations, and our data is available in bit form there, and then we do the decoding techniques, which is opposite of the encoding techniques used earlier, and then we have our information. Then we compare this information with the original information to check bit error rate, etc. So this is the whole basic component of the communication system. Among this communication system, if we pay attention, there are digital domain operations, which is shown by this red arrow here, and then there are analog domain and RF domain. Now, because this course deals with the software defined radio, let us see the limitation of digital versus analog circuits. When we are talking about the analog counter parts and components with respect to the digital components, the analog components have a rigidity, because once you have fabricated them, you cannot configure them. You have to again design a new component in the analog domain and use it. Now, due to fabrication process and different process, analog components are inherently not that precise. So they have limited precision. They are not flexible and they have limited precision, and it includes some distortion in the system, some non-ideality in the system. As opposed to analog system, if we can have a complete digital system, it can be more flexible. If your scenario changes, you can just change the coefficients and you will have a better precise solution there. It is reconfigurable in nature. So whenever your incoming signal changes or your channel condition changes, you can reconfigure it. Even if your frequency changes, in the analog domain you cannot do it because you designed for that frequency. In digital domain, you can simply use the new frequency, you can define it like that. So of course, software defined radio solutions are better than the analog components. So what is stopping us? Basically, the limitations of the hardware components in the transmitter, we want to remove them, and this is the motivation for the digital front end. So software defined radios were proposed initially as a concept of pure digital RF front end. So ideally, it was proposed that we can do everything in digital domain, and after that only we have to do digital to analog conversion and transmit it through antenna, receive it, and then everything can be done in the digital domain. So what is the limitation in this ideal definition of software defined radio? First of all, requirement of very high speed D2A and A to D converters. So we know from our Nyquist criteria that our sampling rate should be higher than twice of the maximum incoming frequency. So when we are dealing with the very high RF components, for example, I have told you that we should work at 2 GHz frequency, so that we have the small antenna size, right? In that case, what should be the sampling frequency of this D2A or A to D? Of course, for FC of 2 GHz, sampling frequency should be greater than or equal to twice of FC plus whatever is the band of that signal. So if this is the FC and this is the bandwidth, theoretically for the Nyquist calculation, this will be the highest frequency. So Fs should be greater than this one. Now if FC is 2 GHz and bandwidth is 10 MHz, you can see from here it has to be easily more than 4 GHz, right? Now this is very high sampling frequency. So state of the art D2A and A to D converters, they cannot have that much high speed, although there are new inventions in the VLSI technology and people are trying to reach it. It is still a limitation, and if we go to even higher frequency ranges, for example mm wave, etc., then of course it becomes a very hard limitation. So There are some way around it, and we will be showing those methods also, how we can avoid this limitation or find solution for this limitation. But the another requirement, which is of the high power to transmit signal to long distances, we cannot avoid RF power amplifier. Now, our RF power amplifier by design is a completely RF component and log component. So, this will always be there, and it has many issues, many distortions related to this component. So, in this course we will also be covering the limitation of RF power amplifier. So, the limitations of the A to D and power amplifiers, we will be discussing this limitation and what can be solutions to this limitation in this lecture further. Thank you.